Hello.
Okay, hi.
So welcome to this session. For the next 3 hours, we're going to look at a lot of Java 9, and specifically about the module system in Java 9. So in the first part of this session, we will look at modules in general. We will start looking at new syntax. We will have a lot of code to look at, and we'll learn how to use Java 9 and the module system to actually create new code in a more modular way. Then we'll have a small break, and after the break we will continue to look at migration, because we probably all have existing code, and although the module system is pretty awesome, it also makes you wonder how to deal with existing code. How are you going to migrate your applications today towards a more modular setup? So that's what we spend time on in the second part of the question of the session. So my name is Paul, and I'm here together with Sander. We both work for Luminous, and we're from the Netherlands. And Sander and I started writing for O'Reilly about Java 9, so that's the book we are working on. The book should come out somewhere before the Java 9 release, or somewhere next year, probably. And we've been doing quite a lot of talks about Java 9 recently. So let's dive right into it. In the first part of the talk, as I said, we will look at how the new module system actually works and what we can do with it. So we will look at, first of all, the concept of modularity. Why should we care about this, and why is it important in the first place? Then we'll start looking at the module system in Java 9. We will start looking at new syntax, and we will learn how to actually create our own modules. And during that process, we will also introduce a new concept called services. Well, actually, that's an old concept because it has been in Java for a long time already, but it gets new meaning in Java 9. So we'll look at that. And along the way, we'll actually show code of a real working application that, actually works really modular. And at the end of that part, we will also look at linking, how to actually create small images specifically for your application, including the JVM. And as I said, after that, we'll have a break, and we'll start looking at migration more deeply. But first of all, why should we care about modularity? Well, something that I've been saying for many years already is that modularity is the ultimate agile tool. And the reason that I say that is because if you don't have a proper modularized code base, well, we kind of all know what happens then. In the first few months of a project, everything is fine, it's fun to work on it, we can make changes really rapidly, but then after a few months, well, you fix a bug somewhere here in the system, and something breaks at some other part of the system that you didn't even know. Maybe you know it existed, but you didn't know there's a relationship between those pieces of code. But apparently there was. And the bigger and bigger the code base gets, the more, spaghetti code you get. And of course, there's all kind of best practices to avoid this. And let's be clear, modularity is a design principle. It's about architecture. It's not necessarily something just about coding. But even if you have this beautiful architecture drawn up on a whiteboard, well, we need some constructs as well in the language and our runtime to actually make sure that this beautiful architecture also shows up in the code. And if you don't have those constructs, well, in many cases, we do see that we get more and more spaghetti code, and after a year or a few years, it becomes harder and harder to work on a code base. If you do have a proper modularized application, a modular code base, it becomes much easier to reason about the effect of changes. So we can reason about, well, if I make a change to this module, it cannot affect other pieces of code, because the code that I'm changing is actually hidden and just encapsulated in that module. And this makes it a lot easier to actually grow a code base, get rid of code when it's no longer useful, and just make changes to it in general. So this is a very important concept, but of course not a new concept. I mean, modularity is one of the oldest design principles in software. So you might also wonder why talk about this in Java after Java has been around for such a long time already? Well, we'll learn about that as well. But first of all, let's look a little bit deeper what modularity is actually about. If you start working on a new application, everyone starts drawing boxes on a whiteboard. And that's a nice abstraction. And if you look at those whiteboards, very often you will actually see something that, well, represents modules, more or less. And the important thing about modules is that we have a bunch of implementation code. So in Java, that would be classes and interfaces. And those classes, those implementation classes, they are, of course, connected to each other. They use each other, they talk to each other, and that's fine, because if you wouldn't have any relationships between classes in your code is probably not doing anything, right? But then when you have one part of your application, something that's doing one function, you actually want to draw a box around it and hide the inner details to the rest of the world. The rest of the world shouldn't care about how a specific function in your system is implemented. And you should be free to actually make changes to that implementation code without, well, bothering anyone else. So we want to draw this nice module boundary around our implementation code. And the only thing that we share to the outside world, and with outside world I mean the rest of your code base, the only thing that we want to share is a service contract. So looking at Java again, a service contract is probably just a Java interface. And you use this service contract to use the functionality provided by a module, but you don't care about the inner details. So what we get with this kind of boundary is that we can make sure that no one is depending on our specific implementation classes, so that we can just make changes to it as long as our service contract stays in place, and nobody should care about it. And that's what we need. But of course in Java we have a problem here, because we don't actually have those module boundaries. There's no concept of modules. And of course we do have packages, and in our classes and interfaces we can use keywords like public and private and protected, etc. to say something about access control to that code. But as we also all know, as soon as you start working with multiple packages, you're kind of forced to make everything public. Most of your classes in general are public. And it becomes very clumsy if you actually want to make stuff private. That's just not easy to work with in Java. So we're kind of lacking this whole mechanism of defining a module. And we can't do any kind of strong encapsulation, at least not in the runtime. Java 9 is going to change all of this. In Java 9 we will actually get a proper module framework. And that gives us the concept of modules in our own code as well. But remember, Java 9 is not released yet. It's currently scheduled for summer next year. It kind of looks like they will make that schedule, so that's very good. But it's still in progress. So a funny fact about the second part of this talk, where we talk about migration, we've been giving this talk, this is the fourth time we give this talk, and for the fourth time it is a completely different talk. So when we started out, we based our findings on a prototype that was out there at that moment. Especially in the area of migration, there has been, well, rather large changes in the past few months. So it's still in progress and there are still changes being made. It does feel like it is stabilizing out. So most probably we will get a code freeze for Java 9 fairly soon, but it's not there yet. So probably most of what you see today will end up in the final release, but of course no guarantees there. It is important to know that there are prototypes currently available, so you can play around with them, and that's what we will use during the talk as well. I highly recommend actually playing around with them. I also highly recommend giving feedback on the mailing list, because they do actually listen to that very well. So definitely do that, and well, get prepared for the release. So if you look at Java 9 and about the module story there, there's actually two main goals they try to achieve with Java 9. The first goal is actually modularizing the JDK itself. The JDK has become really large, and well, there's two problems with that. First of all, it became harder and harder for the JDK team to make changes to, well, this huge code base, because they were getting spaghetti code inside the JDK as well. And they were introducing bugs by changing something and breaking something that should be unrelated, but apparently wasn't. This code base is very, very big. And that means you do need a, well, something like modules to actually manage that code base. So that's one part of it. The other part of it is that for us, it's also a problem that the JDK is as big as it is today, because looking back at Java, they have been adding technology with every release, but they never removed any technology from Java, because backwards compatibility has always been very important, and that means they just added more stuff but never removed anything. Looking at the JDK and the JRE today, it's really big. That means that if you have a user that wants to use your Java application, they actually have to, well, download the JRE. That's quite a big download. And of course, there's also the memory overhead of actually loading this gigantic thing. So it would be nice if you can actually, well, be a bit more efficient there. And of course, in Java 8, we already got a compact profiles, which is kind of a very inflexible way of making this big JDK a little bit smaller. But that's just not good enough. And Java 9 is going to change that. So that's one part of the story. This is just about the JDK and splitting up the JDK itself. The other part of the story, which is probably more interesting to us as developers, is that we also get a module system to modularize our own code. So we will get the concept of a module in the Java language, and that's what we're going to focus on mostly in this talk today. The interesting thing is that we will get the same module framework for our code as what I have used for the JDK internally. So it's exactly the same thing, and there's no magic tricks inside the JDK that gives them well, more power or flexibility than what we will get for our applications. So at least it shows that you can actually use this module system to modularize a pretty large code base. Speaking about the JDK, this is a picture of the modules inside the JDK. You see there's quite a bit of them. And there should be quite a bit of them because, as I said, there's a lot of technology inside the JDK. Every separate piece of technology, you could say, in the JDK is now in its own module. Well, all the way at the bottom we have Java Base, and this is a module that you will always implicitly depend on. And this contains the basic Java constructs, like the packages from Java Lang, and the collections, and stuff like that. So stuff that you kind of always need when you write Java. But anything besides that, anything besides the bare essentials in the Java language, well, you have to start using other modules. And maybe those modules will depend on other modules, and well, by this, the module graph that you actually use gets bigger and bigger. But the nice thing about this is that if you're not, let's say you're not using JavaFX because you're writing a server-side application, or you're not using Corba because, well, hopefully nobody does anymore, you don't actually need that anymore. You will not need to load those, well, those parts of the JDK because, well, you're not depending on that module. The other interesting thing that we see here is that there's, of course, lots of arrows, and these are dependencies between modules. And as we will see in a moment, dependencies between modules become really important. We have to specify what we depend on. And this is not just this implicit classpath thing anymore that we're used to today. And you, if you look at it closely, you'll also see that all the arrows are just pointing one way. There's no cycles in this whole graph. That's important as well, because you never want cycles in a modular system, and actually that's completely forbidden in a module system in Java. This was just about a JDK again, but the thing that we will well, notice even more as developers is the fact that the classpath is going to disappear. Well, don't worry. In Java 9, the classpath is actually still there. You can still use it, and you can use the classpath as you would use today. But in that case, you're actually not using the module system. So you can choose to just ignore the whole module story and just keep running and building your applications as you would do today on Java 8. That's fine. And we'll actually look at that later as well. But next to the class path that we already know, there's a new concept of a module path. And the module path is not just this long list of classes like the class path that will be scanned from left to right until you find something matching, but it's much more reliable, and we'll see in a moment why it's more reliable. And this is great because, I mean, Java is pretty good, but I don't think anyone really likes the class path, right? It's completely unreliable. Looking at a class path like this, and this is not even a, well, this is not even a very a very exciting one. But it's pretty much impossible to say, first of all, what this thing is doing, but it's even harder to say if it's complete. Are we missing any classes? Well, I don't know. Are there any duplicate classes in duplicate versions? I don't know. Yeah, how do you figure that out on a list like this? And the problem is, JRE also doesn't know. When we start our application, it will just start loading classes. And if it happens to miss one, well, we get a runtime exception. And we all know those class not found exceptions that, well, some unlucky user gets hitting a specific code path in our application. That's not very good. We want to have this much more well-defined, and we want to get early errors, and that's what we get with a new module path. So instead of working with a class path, we will start defining modules. And a very important property of modules is that they have to be very explicit about what other modules they depend on. So if I'm module A and I want to use classes from module B, I have to explicitly say that I require module B. And because I have to be explicit about this, in all phases of development, which means build time but also runtime, the JRE can actually verify if our system is complete, if we have all the modules on the module path that we actually need to execute this application. That means also at runtime. So when we start an application and some modules are missing, we will get an early exception instead of, well, waiting for it to blow up at some point. So that's really good. That's a big step forward. The other thing that we will get with modules is encapsulation. So looking at an example, Java base in this example. Java base, as I said, contains all the core Java classes, so to speak. A lot of those classes are, of course, meant to be used by other modules. You're meant to be used to collection classes. That's fine. And those are public. You can use them from other modules. But there's also a lot of internal implementation classes in the JRE that you're not supposed to use. Anything that comes from the Sun Star or com.sun packages, for example, you're not supposed to use them. And it has been documented, well, since they existed, but of course everyone ignores that, and whenever you find something interesting in those packages, you will probably use it. So there's a lot of existing code out there that uses well, packages from those private parts. Well, not anymore in Java 9, because in Java 9, those internals will actually be encapsulated, meaning that you can't actually access them anymore. We will talk about workarounds, etc., because you can work your way around it, but by default, there's proper encapsulation, both for JDK classes, but also for your own classes. That's very important. And then before we dive into lots of code examples, there's always this question, okay, why come up with a new module system? I mean, Java has been around for so long, and we kind of survived. And there's a bunch of module systems like OSGI out there. Why would we invent a completely new module system? Well, the first problem with something like OSGI is that it's built on top of Java, right? It's built on top of the concept of the class path, for example. So it's kind of impossible to modularize the JDK itself with a technology built on top of the JDK. You're just at a long layer in the stack, so to speak. So that's not going to work out. But then, of course, you can still argue, well, that's great, but it's not really my problem that I want to modularize the JDK. Let them just modularize the JDK any way they like, any technology they like, applying every hack they can possibly come up with, that's fine. Don't bother me with it. I'm happy with Java as it is. And if I want something like modules, I will just use OSGI. And that's a pretty, well, that's a good discussion. And you can have this discussion both ways. But even for someone like me, I've been using OSGI for many years and wrote a book about it. It's hard to deny that OSGI never became really popular. Even if it's a good technology, it's still just not used very, very often. And the problem with that is that tool vendors and library authors always kind of see it as a second-class citizen. They don't really care about OSGI users so much. Well, this is of course a vicious circle that we'll never get out of, because if people actually want to use OSGI, they need tooling, and the tooling is not there, so they will not use OSGI, and well, that's a big problem. With Java 9, there's just no way around it. tool vendors and library authors will have to deal with this, no matter they like it or not. But this is good because in the end that will force the ecosystem to move towards modules and have proper support for it, making the story a lot better for everyone. So that's at least one important point. Right, enough talking for now. Sandra is going to show us an actual application with Java 9 modules, so go ahead.
So Paul, this all sounds great in theory, but I guess we're ready for some code. And we have code, we have examples using the Jigsaw prototype that Paul talked about. And you can also download the prototype and play with it, just like we did. But I guess you're all sick and tired of Hello World examples. So we're going to introduce an application that we call Easy Text, which is a bit more interesting, which is a bit more involved than the Hello World. And what it does is that it can read in a text file, it can analyze it using a given algorithm, and it can give us back the complexity of the text. I wonder why we need that if we're writing a book. Okay. Anyway, we have two modules here that we're going to look at. And the first one is easytext.cli, which is the command line interface, which does the reading of the file, does the parsing into sentences, and it will pass this to the analysis module, where the actual algorithm lives that does the analysis on the text. So here we already see that we can have interaction between two modules, and we'll see how the boundaries between those two modules actually work. And we're going to do that based on this example of text analysis. So there we go. We're going to switch into the development environment. And the first thing you might notice is that this is not an IDE. It's not Eclipse, it's not NetBeans, etc. That's not because I don't like those. I like some better than others, that's true. But in this case, we have two reasons for just using a plain text editor, like Atom in this case, to show you what is changing in Java 9. The first one is that it's a very practical reason. The current IDEs aren't all really geared up yet for Java 9, especially for the module system prototype. There's lots of changes going on, as Paul already said, and they're just not keeping up yet. So I would show you lots of red squiggly lines if I were to use an IDE, which is not very nice. And the second reason is, by using an IDE, you abstract away lots of things. And what I'm going to do is I'm going to use the Java compiler directly and the Java runtime directly to show you exactly what has changed as opposed to how it was in Java 8. So that's the reason we're in a very simple environment here. You can already see I have a source directory with two nested directories. And normally in a source directory, we would have our packages, our package structure. But in this case, we have two module directories. And you can see the names, they correspond to the modules that I've shown in the slide, Easy Text Analysis with the algorithm and CLI. And if I open such a module directory, you can actually see why it is a module directory. Because there's a module descriptor in it called moduleinfo.java. And also, inside the module directory, we have this package structure that we all know. So we have Java Modularity, Easy Text, CLI with a main class. Now, if we look at this module descriptor, it's very bare bones, right? We have a module keyword, we have the name of the module, and then nothing yet. However, we're going to extend this and make it work together with the different Easy Text Analysis module. I said module is a keyword, and you might be wondering, okay, what does this mean for my existing code, where we already have identifiers, maybe named module? Well, you're in luck, because it doesn't affect that. Module is only a keyword in the context of the module info. So just here, we have the module keyword, and this holds for all the new keywords that I will introduce in the context of this module descriptor. Those are contextual keywords, and they won't affect existing code using identifiers with the same name. So that's good. Now, if you look at the analysis module, there's also a module descriptor, which actually makes this a module, and it's named Easy Text Analysis, nothing surprising here, and it contains a class that we call Flash Kincade. Flash Kincade is a popular text complexity metric, and it implements the analysis that we're going to use. So let's look at the main class then. As you can see, we have some imports from basic packages from the Java runtime. So like Paul already said, there's a Java base module, which you implicitly depend on, containing all the basics of Java. That includes the NIO packages, IO, util, etc. So we don't have to say anything about requiring any other platform modules in this code. Now we do have an import saying I'm going to use Java Modularity Easy Text Analysis Flash Kincade, which is right here in the other module. And what the code does is that we're going to read in an argument, which is the file name that we're going to read. We're going to read the file, going to chop it into sentences, and we're going to instantiate this FlashKK class, which is coming from a different module, and we're going to call analyze on it with the sentences that we parsed. Sounds reasonable, I think. So what we're going to try and do is compile this. There we go. And what I'm going to use is a new flag called module source path. I'm going to point it to a source directory. And this module source path flag allows us to compile multiple modules at once with the Java compiler. Now, because we're compiling multiple things at once, we also need to specify an output directory where it's, the classes are put. And this is something that probably a lot of people may have forgotten already, because we're typically not using the Java compiler directly, but we're using Maven or Gradle to do that for us. But when you invoke the Java compiler, you need to pass in all the files that you want to compile at once. In this case, these four, the module infos and the FlashKK and main. Now, I'm not going to type those all out, so I'm going to use a little trick here. Find name, start with Java. But this just lists the four files that I just pointed out. And we're going to compile them together. And we're providing all the files, so it should work, right? So there we go. And what we see is that we get a compiler error. And this compiler error says, FlashKK is not visible because package Java Modularity Easy Text Analysis is not visible. Which is kind of interesting because we explicitly have the class here and we import it in our main. And in Java 8, this would have just worked, right? In this case, Paul already said we need to be explicit about what we require in a module. So what we need to do here is that we say we require easy text analysis, meaning that we can use code that is public and exported from this other package. So why is this a good thing? It makes you think about what your dependencies are explicitly. You can't just import some class from some random module from the JDK or from some random module in your application and start coupling yourself to it, which is good, because that's how spaghetti code gets born, right? You don't think about it, you just use a class and it does what you want to do and you're done. But actually, you may be violating your architecture and your nice modular structure of your application, which comes back to bite you when you really want to make changes on the other hand of the class. So, now that we've done this, we say we have required the easy text analysis module. Let's try to compile it again. There we go. And unfortunately, we're still getting the same error. So as you can see, it's still complaining about the visibility of this FlashKK class and the package that it lives in. And the reason for that can be found in the module descriptor of the easy text analysis module. What we see here is still empty. And by default, all packages that are not explicitly exported in a module descriptor are encapsulated. And as you can see, encapsulation really means that it's not visible to other code in other modules, even though this FlashKK class is a public class. Just let this sink in, right? We have a public class, which is just in a package, but we cannot use it unless we explicitly export it. So that means we need to be really careful about what is the API of a module. What are we allowing for outside use, and what are we only allowing for internal use in a module? Now in this case, we know that we want to expose this FlashKK class, so we're going to say exports Java Modularity Easy Text .analysis, which is the package name. So exports works at the package level. We're saying I want to export all types that are in this package from this module, whereas requires works on the module level. You say I want to require another module and use any of the exported packages from this module. And now that we have the exports and the requires in place, we can compile again, and we actually have a successful compilation. So what's going on here is that we are forced to be explicit about what other modules we need from the CLI module, and we're also forced to be explicit about what packages we want to expose to the outside world as API of our module, in the case of this analysis module. So now with these two things in place, we have compiled modules. And if we inspect the output here, we can see that there's a module info.class. So this is the compiled version of the module descriptor, which means that this information, this explicit information, is also available at compile time and at runtime if we're going to run these modules. So that's going to be the next step. If we want to use these modules, we're going to use the Java command, and we're going to use the module path rather than the class path. So in this case, we're saying that the compiled modules that we have are the module path, and we're going to start not just a jar file, so we're not going to say -jar, but we're going to say -m for module. We're going to start a module, and we're going to start the easytext.cli module. Now, if those two modules were packaged into a jar, and I would have set the exact main class entry of this easytext.cli jar, then this would be it. Then the VM would know enough. But in this case, they're not jars, and there's no main entry defined yet. So I have to specify in the command line explicitly which class I want to start from this module. So in this case, we're going to start Java Modularity easytext.cli.main. And it works. We got a welcome message that says, okay, please provide a file name. There we have it. I'm going to feed it chapter 3 of our upcoming book. And it says, okay, I'm going to calculate the flash Kincaid score, which is 60 in this case. And I'll leave it as an exercise to the listeners to find out whether it's actually complex or not. But we have working code using modules. Now, I hear some of you thinking, okay, what's in the name? Instead of class path here, we now say module path, but what is the big difference between those? And I want to illustrate this by throwing away one of the modules on the module path. So what I'm going to do is I'm going to remove the analysis module. There we go. So now we have a module path containing only the CLI module. And I'm going to run the same command again. So we're going to run the same module in the same class. And what we see is that this will fail at startup. And we get a resolution exception saying, so you want to start module easytext CLI, but this needs easytext analysis. And I cannot find it on the module path. So I'm not going to start the application. Please fix this. And this is much more powerful than the class path, where we would just randomly at some point blow up when a class was loaded. That's not on the class path. Now, what we see here is that the explicit information that was used to force us to be to do the correct thing at compile time also helps us to create a reliable composition of modules at runtime. And as you can imagine, when your module graph grows, so now we have 2 modules, which is fairly trivial, but this works recursively, transitively, so this is really, really helpful in larger systems. And that's what we want to do modular development for, because we want to build large systems that are manageable. So let's wrap this up and go back to the slides again. This was our first demo, and it shows how we can create 2 modules, how they interact, what exporting a package means, what requiring a module means. But still, you might be wondering, there's a very tight coupling going on between those 2 modules, right? We exported this implementation class, flash Kincaid, and we exposed this to the CLI module. And this CLI module instantiates it and calls a method on it. But what we rather want to see is that the CLI module doesn't really know about this implementation class, but it only knows about, let's say, an analyzer interface. And this analyzer interface then has the analyze method, and that's all the CLI module needs to know. And somehow it would obtain an implementation of this interface, and it will use that without knowing the exact type of the implementation. So in the abstract, we would want to say something like, my interface I is something, because we don't want to instantiate the implementation class directly, because that would mean that the implementation class needs to be exported from the module, like we did in the last example. And that's something that we don't want. We want to export the interface. We want to have a public interface, a contract between the CLI module and the analysis module. But we don't want to expose the implementation class, because that's our implementation details, and maybe it's even multiple classes instead of a single class. We don't care. But we want to have an instance of the interface without knowing the implementation. But that's going to be hard, because how are you going to access an instance if you can't access the type and instantiate it? That's the big question. And of course, like all great problems in computer science, this can be solved by adding another layer of indirection. And in this case, the layer of indirection, we shall call it the service registry. And this is a simple inversion of control pattern, right? We're going to say, okay, we're going to have provider modules that provide implementations. We're going to have consumer modules that consume those implementations, and those need to be decoupled through the service registry, where a provider module can say, here's my implementation for this interface, pass it to any consumer that needs it, and the consumer can say, hi, I'm interested in implementations of this interface. Please pass me back instances without me having to know about their exact types. If you take this further, of course, this ends up as a pattern that we also know as a dependency injection, where you can even use frameworks to inject those dependencies for you. That's not what Java does out of the box for you. I mean, there are frameworks for that. But out of the box, what we're going to look at is the services in the Java 9. Out of the box, we get a service registry where you can look up instances without knowing their exact type, using the interface as contract between providers and consumers. So before we apply this to our easy text example, let's look at a more down-to-earth, simple example. And here we have a module myAPI, which exports a package ComAPI, presumably containing an interface, my service, or my interface, or my service, I don't know. Doesn't matter, but it exports just the interface. And this is the shared contract between the provider and the consumer of a service. Now, if you want to have a consumer module, you can just declare another module, in this case my consumer, and it requires my API because it needs to see the interface type that lives in the ComAPI package. But then you see there's a new statement added in the module descriptor, uses ComAPI my service. And this uses expresses to the module system that this module is interested in instances of the ComAPI my service interface. And it wants to have instances without knowing the exact implementation types behind them. Now, if we have a consumer, we also need to have a provider, of course. And this provider looks a bit similar. It also requires my API. And it requires it because it needs to implement this interface. And then there's not a uses, but a provides constraint. And it says, I provide something of type ComAPI my service with a specific implementation class, my provider.my service impl. And this my service impl obviously implements the my service interface. But a big thing to note here is that the my provider package is not exported from the my provider module. So it's encapsulated. So on its own, the my consumer can never reach this my service impl class. However, through the service mechanism of the module system, it can request any instances from any providers that implement this service interface. And then the service registry can do the instantiation of my service impl because it does have this superpower to instantiate something that's encapsulated. And then we will provide it to the module my consumer. Now, the last question to answer here is, okay, in my consumer, how do I actually get access in code to those instances of my service? And that's with the service loader API, which has been enhanced to be to make use of those module system constructs. So what we have is a service loader.load call, where we pass in the service interface type, myService.class in this case, and you get back an iterable of instances of this service type. Now this service loader call, and Paul already said this in the beginning, has been part of Java for a long time already. However, the mechanism to use it has been to have a file in the meta-inf directory of your jar pointing to the implementation class and given an interface name. And this mechanism is used in the JDK internally, and some frameworks do use it, but generally in application development it hasn't been very widespread in use. We think that will change with Java 9 and the module system, making it easier to use. So in this case, you get back an iterable of all the instances, and keep in mind there can be 0, 1, or more instances. There's no guarantees on that, so you will have to need to deal with that in your code. And you can iterate over this iterable and call methods on the surface. So we're going to apply this to our demo again, and this is because I want to show you how you can use services to make the system extensible. and this is also one of the goals that we at least have when we design and create modular applications. We want them to be future-proof, we want them to be extensible. So in this case, I want to show you that if we introduce such an analyzer interface, that we can have multiple implementations of it, and those are decoupled at runtime through the service loader, and they can be used independently, and you can just compose your application together depending on what your needs are. The other axis of extensibility is reuse of modules. And I want to show that by introducing a graphical user interface on top of the same analysis implementations that we also use in the command line version. So there you can see both how we can create a module that's a GUI, and that will obviously use more of the platform, the JDK platform modules. But at the same time, it reuses the same backend modules as we have for the CLI implementation. Before we dive into the code, I want to show this diagram, just to get it all straight before we see the code itself. And what we did is we introduced the EasyText algorithm API module containing the analyzer interface, which is our contract between the front-end modules, which are the CLI and the GUI modules, and the back-end modules, which are the Kincaid and the Coleman modules here. So all the arrows here indicate requires relations. So the front ends require the API module because they need to know about the interface type in order to call a method on it. And the implementation modules depend or require the API module in order to implement the interface. But the big thing here is there are no arrows, no requires relations between the CLI, a GUI, and the two implementation modules, which means that they are related, of course, at runtime through the whole service loader mechanism that I showed. But this kind of coupling is much nicer than the hard coupling of the requires that we had in our first example with the two modules. Because if I were to add a third analysis algorithm here as a third module, I do not need to change anything in the CLI and the GUI modules. They will just be able to pick up the new implementations through the service loader. Now, one last thing to point out here is that the EasyText GUI module that we're going to look at now contains two other dependencies besides Java base, which is implicit. It also depends on JavaFX graphics and JavaFX controls now, which sort of gives away that we implement our GUI using JavaFX, of course. So let's look at the code and see what it looks like in real life. So here we have our source directory, again, containing multiple modules. And here we have the API. I'm going to open that first. So the most interesting part of the API package is the analyzer interface. And this is just a plain Java interface. There's nothing module system specific here. There's nothing service loader specific here. It's just a plain interface with the get name that we can use in the GUI, and the analyze method where we can pass in our sentences with words, and it will be analyzed and it will give us back a value. That makes the module descriptor for this module very easy. We're going to export the only package that's inside of this this API module because we want people to use this interface. Now, if we look at the GUI implementation, we see that there's a main class as well. And there's much more imports than the CLI version. We import all kinds of stuff from JavaFX. That's also why we need the explicit dependency on the JavaFX modules from the JDK. But when we look at the imports from our own other modules, we can see that it only imports from the algorithm API package coming from the algorithm API module. And it doesn't have any direct relations to the implementation classes that live inside of the Kincaid and Coleman modules right here. So just to satisfy your curiosity, there's just an implementation class here that implements the analyzer interface, of course. And for the rest, again, there's nothing module system or service loader specific here. It's all just Java code as you know it. So going back to the main, let's see how we're going to find our analyzers. And now they're null, but of course we're going to use the service loader.load call here. I'm going to say I want to load all instances of the analyzer type. There we go. And then we're going to look at the module descriptor. So we have module EasyText GUI. It requires JavaFX graphics and controls for obvious reasons. It also requires our algorithm API, and because we need to know about the analyzer interface. And then we need to declare that we use the Java modularity. Oh, there we go. Java modularity EasyText algorithm API analyzer. So we're going to indicate to the module system that we want instances of this type. There's one particularly interesting line that you've probably already seen that says that we need to do something special for JavaFX here. And that's interesting. What happens is that this main class extends application, which is a JavaFX class. And then you call launch. And under the covers, what this does is that it tries to reflectively instantiate our main class. So think about it, there's code living in the JavaFX graphics module that is trying to access code in our module. And that doesn't work by default, because by default, our main class is encapsulated because we don't export it. Now still, JavaFX graphics would like to access this code because it needs to instantiate it to show our application. So we have a couple of choices here. We could just say, okay, we're going to export our GUI package then, just so it's available to everybody, and it can be used by everybody. And that's not really satisfying, of course, because we don't intend this to be API of our module. It's just that at runtime, we want the JavaFX graphics module to be able to reach this code. So what we can do is we can do a qualified export. We say exports this package to JavaFX graphics, meaning that only JavaFX graphics is able to reach into code of our EasyText GUI package here. So that's a fairly nice solution. Later in the second half of this university, we'll see that there are other ways to do this as well, which are even nicer, but are a bit too advanced for now. But anyway, this is just to make sure that JavaFX can reach into our main class to reflectively instantiate it. So let's run this code. And I'm going to use a script just to save some typing here. That's creating jar files of all the modules and then going to start it. Then we have our application. And we have some sample text. And the idea is that we would have analysis implementations here. But that doesn't happen yet. We have an empty list. So that's a bit sad. And that has everything to do with the fact that we did declare that we use the analyzer instances, but our provider modules also need to declare their provides. So let's do that. We do a provides of Java Modularity EasyText algorithm API analyzer. And we're going to provide it with the class that implements it, in this case, the Coleman analyzer. So Java Modularity EasyText, I'll go Coleman, the Coleman analyzer. There we go. And this makes sure that the service registry knows about the implementation that we have. I'm going to copy this to the Kincaid as well. And the interesting thing here to see is that Kincaid itself also uses another service to implement its own service. So this also works transitively. But here we want to add a provide statement saying, okay, we're going to provide the analyzer with, in this case, the Kincaid analyzer from the Kincaid package. So note, there's no export statement here. So we cannot just go reach in to this Kincaid analyzer class. We can only provide it through the service loader, through the service registry. Now if we're going to run the same application again, there we go. You can see it's already bigger, so there should be something in here. And indeed, we have the two implementations, Flash Kincaid, which we can use, and we get 80 on the sample text. And we have Coleman Lyon, which is an alternative text complexity implementation, and we get 7.5, which is obviously on a different scale, but that sort of proves our point that we have extensibility now. I will also show you that this is a very dynamic model. So if we're going to look at the compiled jars here, what I can do is I can just throw away, for example, the Kincaid jar. So we're going to delete it. Yes, please go. And we're going to run the application without recompilation, without doing anything. We're just going to run it again. And now we only have a single implementation that we can choose from. And the same, of course, works if you add multiple implementations to your module path. So this is a very flexible way of combining together services in your application without being hard coding them between the modules. Okay, so I think the idea behind services is clear. The idea between extensibility is clear. So let's go back to one of the features that I think is very, very cool in Java 9, which has never before been possible in Java, which is linking. And linking is a new development phase that has been added to your Java development toolkit, so to say. Keep in mind, it is an optional phase, so you don't need to use linking. But you can if you have a modular application, if you have an application that's built of Java modules. So what we get is a new tool called JLink, and you can use this new tool to create a custom runtime image. And you may be wondering, okay, so what is a custom runtime image? So think about it as a JRE containing only the modules that your application needs from the platform, plus your modules directly compiled into it as well. So you can just ship that, you can distribute it, and it will run your application, and it will be no bigger than just the modules of your application, plus the modules that you need from the platform. You don't need to do anything special to create such a runtime image, because you already put all the metadata, all the information into the module descriptors. So it can take your module and it can trace all the require statements and see what it needs from either other application modules or platform modules. And that information is used to create this custom runtime image. So on the one hand, you can create something that's nice and small. And on the other hand, there's also a new opportunity here. And that's the fact that we have a new point in our development phase where all the code of your application and the platform comes together. Meaning, it's also a new opportunity for whole program optimizations across class boundaries, across module boundaries. So I'm not going to go into that very deeply, but think about optimizations like dead code elimination or other stuff that really needs global information to see what's going on and to actually be efficient and applicable. So this is something that JLink can also do. The nice thing about JLink is that it's plugin based, so we don't need to wait for the JDK or the Oracle team to implement those optimizations for us. Even after the release of Java 9, you will be able to create new plugins to JLink that either transform or optimize this runtime image. So without spending much more time on it here, let's go back to the code and see how that works with our EasyText application. And for this, I'm going to do the jar run one more time so I have all my jars back that I just removed. Because we're going to need those for the runtime image. Okay, there we go. And what I'm going to show you is an invocation of JLink, where we set the module path to our compiled and jarred modules. In this case, this list of modules. But we're also pointing to a jmods directory inside our Java home. And this is the location where the modules of the JDK itself live. And it's interesting because we didn't have to add this to the module path in the compile and the runtime situation that we just saw. So what's different here? Well, the difference is that we need to explicitly point it at the JDK that we want to create a runtime image for. So if I were to download a Windows JDK onto my Mac and point the JLink tool to the Windows JMod directory, I would be able to create a runtime image that runs on Windows. And This works for any architecture and platform that there is a JDK defined for. This also means, obviously, that the runtime images that we're creating are architecture and operating system specific, but that, of course, makes sense after my explanation. The second thing that we see here is that we're going to add a module to the image, in this case, our EasyText CLI module. And what happens is that JLink takes this CLI module and will analyze this module descriptor and recursively add any modules that are required by the EasyText CLI up until the last module is added to the image. Furthermore, there are some options to strip debug symbols, compress the image, make it smaller, etc. All kind of interesting if you want to distribute and use this image. So let's just try this out. And there we go. It takes some time, especially since I added compression here. And what we get now is an image directory containing a bin, conf, include lib. And this sort of looks like a JRE, right? So if we look inside the bin directory, we see that we have the Java executable, the key tool, which apparently comes from some Java base tool that's also in the image, and also a convenience wrapper around our application, EasyText CLI, that we can invoke directly without setting any module paths or without setting up any class paths or whatever. So if I run this, I get the welcome text that we've seen before. And if I try this on some test input, there we go, something peculiar happens. We see that it's reading the test input, but it doesn't output any metric. And if we look at the source code, and here's the CLI code, there we go. If we look at the source code, we can see that what happens is that we, again, use a service loader API to load any analyzer instances, and apparently there aren't any instances here. Which is interesting, because we do have the compiled service providers here in the jar directory, but somehow they don't appear to be part of the image. We can confirm this by using the Java command that's inside the runtime image and saying, show me all the modules that are in this image. And indeed, we see that we have Java base, EasyText CLI, which is the one we explicitly added, algorithm API, because it's required by the CLI module. But what's missing here are the service implementation, the service provider modules. So it appears that JLink does use the requires relations to build up the whole module graph. That should be part of the runtime image, but it doesn't use the uses and provides clauses in the module descriptors. And that's in fact the case. That's what happens. You can argue whether it should do this or not, and honestly, for both sides there are good arguments, but this is just a choice that's currently made by the JLink tool. So we can work around this, we can solve this by being more explicit about what we want to add to this image. So in this case, we add the EasyText CLI module, but we also add all the service provider modules that we want to have as part of the runtime image. So we recognized Coleman and Kincaid, and we already saw that Kincaid also uses a syllable counter, so we're going to add an implementation provider module for that as well, and we're going to put that into the image. And again, if any of these three modules would have dependencies in the form of a requires relation, that will be automatically be handled by JLink, so that these would end up in the image. Now, if we go to the image again, image bin Java list modules, we can indeed see that we now have the correct service provider modules. And if we're going to run the application again with the test input, we actually get our two metrics that we expected here. So that's good. But the interesting thing, of course, is how big is this image? And you can see it's just 21 megabytes, which is quite different from a full JDK installation, which is over 400 megabytes, which is, of course, not really the most nice comparison because the JDK always contains more tools than the JRE. But even if you would compare this to a vanilla JRE with all the modules in it, it will be much smaller. Now, as a last point, I want to show you how to create a runtime image for the GUI. And the only thing that's changed here is that we don't just put the CLI module into the image, but we're going to put the GUI module into the image. But of course, we expect this image to be far bigger because it contains the JavaFX parts that we need, and probably these JavaFX modules themselves have dependencies on other modules from the platform too. So we can confirm that it's actually bigger by looking at the image size, and yes, it's 49 megs instead of the 21 where we only had the Java base platform module. And the interesting thing here is, of course, what is inside. And we're going to use the list modules flag again to see that. Here are our own application modules and the Java base, which we already had. But you can see that these JavaFX graphics and control pull in lots of different dependencies from the platform as well. So apparently to use those two modules, you need JavaFX base, you need Java XML, Java prefs, Java desktop, data transfer is getting more and more sketchy now, and JDK JS object. Okay. Who would have thought you needed that to display a GUI? But anyway, because all those modules in the platform have their explicit dependencies in the module descriptors as well, JLink can just traverse the whole graph for us and get this smaller subset that runs our application, which in this case is this list of modules. So we're nearing the end of the first part, and those were the demos for the first part. What I would like to point out is that now is the time to look at your own code and to prepare for Java 9. And there are some tools, and we're going to talk about those in the second half of the university talk as well. For example, JDAPS. You can already use that in Java 8. It's already distributed with Java 8, and it can find code in your code base that uses, for example, internal implementation classes of the JDK. And if you have such instances of usages of internal classes, you should do something about that. You can do two things, and we'll talk about it in more depth after the break. But you can either use a command line flag such as that, listed here, to sort of work around the fact that some things are not exported. Or you can, of course, fix your code and use public and documented APIs, which also sounds like a good plan. But, well, it's not always possible. I know the reality of things. But anyway, if you use JDAPS, you at least find out about the parts of your code that need attention. What we're also going to look at after the break is how you can migrate to a modular world in Java 9 from the existing classpath world. But you don't have to do it as a big bang. There's a sort of gradual migration path possible here, which is very nice, and it allows you to sort of mix your current class path situation with the module path and modules. Of course, you will not get all the benefits of a modular application if you do so, but at least it helps you to get started and get on the right track, using things like automatic modules, which we'll discuss later as well. What's also interesting is that there are still some open issues, some open design issues in the module system. There are also some issues that were open that are already closed. For example, it is currently possible in the current prototype to have optional dependencies on modules. For a while that wasn't possible, and there are some good use cases for that. We've so far also talked about encapsulating classes and code, but what about resources inside your modules? I mean, you probably need some way to encapsulate those as well. That has been addressed in the proposal for Jigsaw 2. Another very interesting one, and something that we also touch upon in the second half of this talk, is about reflection. And we already saw a little example of that with the JavaFX module that wanted to instantiate our GUI main module, and it couldn't do so because it wasn't exported. So we have lots of frameworks in Java that do use reflection. And we can argue about whether that's a good thing or a bad thing. Certainly it's not all good, at least in my opinion, but the fact of the matter is those frameworks are there and they use reflection, and we need to do something with that. So there's a proposal currently, and that's implemented only about 1.5 weeks ago in the prototype, and we're going to show that in the second half, that sort of tries to balance between strong encapsulation and still allowing at runtime reflection into your modules. Another very hot topic is versioning of modules. We saw module descriptors that described a module with a name, but there was no version. And it sort of sounds obvious to have a version on your module, right? And then if we have versions, we can probably maybe also solve the having multiple versions of the same library problem. Well, no. At least not for Java 9 in the current state of Jigsaw. What currently happens is that you can have versions of modules, but they're just annotations. It's not used in any of the resolving of module graphs, etc. So they're just there for information. And the idea is that your current build tools are really good at doing version selection, right? So Maven can solve conflicts for you if you have the right instructions in your POM to make sure that the right jars end up on the class path, or in this case, the right modules end up on the module path. So the big idea here is that the module system isn't going to solve the whole versioning and version selection for you, because that's really not a solved problem. There are multiple approaches. There's one approach in Maven. There's other approaches in different build tools. So this is pushed out into the build tooling side of things, and then the module system will just check whether a module path is consistent. So if you have two modules of a different version on the same module path, it will yell at you and it won't start. But it won't try and pick the right one. Because picking the right one is really rather hard. It's even impossible in the class path situation to have multiple versions of the same jar. It's possible, but it's not supported, right? We get all kinds of errors if you have two jars of different versions. And if you want to really deeply solve this, you can have a model like, for example, in OSGI, where you have a class loader per bundle, per module, and you can have multiple versions of the library, and then you get all kinds of very interesting wiring problems between your bundles. They just, for now, chose to say, this is a problem that we're not going to solve with the module system. So to wrap this up, the first half, if you look at the JSR of the module system and the promises that it holds, we really think that this will be the one chance that Java has to become a really modular platform. OSGI tried it. I wouldn't say it failed, but it also didn't really succeed. But if we have it in the language itself, it will really force tool vendors, IDEs, etc., to deal with it and to embrace modules, to support them, and to actually help us develop in a modular way. And not just on the whiteboard, but at compile time, as we saw in the first demos. So we need to be explicit about our dependencies. We cannot just have accidental dependencies on parts of our system anymore. But also at runtime, right? And even in the new link phase. So modularity brings us a lot in different phases of development. And in the end, I would say having the spotlight on modularity is definitely a good thing for us as developers. So that's the first half. Like Paul already said, we're currently working on a book for O'Reilly, which contains lots and lots more details about the module system. It's even already in an early release access available on O'Reilly.com. So if you're interested in that, definitely check that out, and the link has some more information. We also curate a Java Modularity Twitter account where we tweet out all the news information about the module system and Java 9 in general. So you're welcome to follow that as well. And with that, I think we're going to go on a break for about half an hour, and I would like to see you back in half an hour. Okay, welcome back everyone. So this is the second half of Java 9 Modularity in action. And as we said, this half is going to focus on migration. Of what do we do to take our existing code, pick it up from Java 8 and run it on Java 9, first of all, and then also maybe even migrate it to modules. So what would it look like if we were just to think about it ourselves? Let's say we have an application that's running on Java 8, with the class path, of course. Here it's undefined, but it doesn't really matter what's on there. We start our app just as a jar. So what would it look like ideally on Java 9? Well, ideally it would look like this, right? So we have the same command with the same class path in Java 9. We have our own application that should still run, right? Well, There are some caveats here. It should work like this, but if you're using frameworks, like for example Spring or Hibernate, and I know a few of you might do that, we did as well in the past life, you will run into some issues. And we're going to talk about those issues. So first of all, in this second half of the university, we're going to look at what it takes to migrate an existing class path-based application from Java 8 to Java 9. And it's not always as simple as I just shown. It could be that simple, but it isn't always. And after that, we're going to look at how this application could ideally look like in a modular world, in the Java 9 module system world. But to get there, we need to take steps. We need to take incremental steps. So Paul will take us through the steps that are necessary for this class path-based application that is using Spring and Hibernate and all the cool tools that we are using currently in Java development, and how we can take this and migrate it step by step into a modular world. And then you should also start thinking, of course, about what does it actually mean to modularize my own application, and how can I get the benefits of the module system and not just the drawbacks of the module system. So these are the topics that we're going to cover in this second half of the university. I hope you'll still enjoy it. And first, let's just try this, right? I mean, shouldn't be that hard. So what I'm going to do is I'm going to switch back to our demos. And as you can see, we have 4 demos for you, 3 of which we will talk about in this second half of the university session. All the code will be on GitHub. We'll have a link in the end. And first, we have a simple class path-based application. So it should be familiar, right? Ooh, it's a lot of dependencies. So this is a Spring-based application. And it's fairly simple, but it's not that simple that we only have a single class. We have multiple classes. We have a main class that bootstraps an application context. It looks up some beans, invokes some methods on those beans. In this example, we have sort of a bookstore where we can create books in a book service. We can retrieve books. We print it out. We have a store service where we can calculate the price, including the tax, and we print it out as well. So the book service underneath uses Hibernate. That's in the books implementation here. So you can see that we have some entities. For example, the book entity, which is just JPA annotations. We have a corresponding service, which is a Spring transactional repository with dependency injection. I mean, this looks fairly typical, right? For a Java application nowadays using Spring and Hibernate. So what I'm going to do is I'm going to take this code, which is not modularized, it's just Java 8 code with all these libraries on the class path, and we're going to try to run and compile this on Java 8 first, just to show you that it actually works. So we have a Java 8 version here, and we're going to invoke this run script, which compiles with this huge class path, and it runs with the same class path and the compiled modules, and it runs our main class. So there we go. It's starting Spring, and it's creating some books with Hibernate, retrieving them, calculating the total price with tax, etc. So that works, right? So what we're going to do is we're going to switch to Java 9, which, by the way, isn't 1.9. We're finally dropping the 1 prefix, so we have version 9 of Java. Yay. There we go. And to prove it to you, I'm going to show the version here, which is hot off the presses. So this nightly build 142 is a couple of days old, I think. So hope it all works out. But anyway, we have a cutting-edge version of Java 9 with the Jigsaw prototype, which is something to keep in mind. There are 2 downloads on the JDK, on the OpenJDK side. One is of the OpenJDK sort of main trunk. It does contain parts of the module system, but it doesn't contain all the latest features. The other one, the other build, is called the Jigsaw build, and it includes all the last cutting-edge features of the module system. And that's the one that we're using and showing right now. So what we're going to do is we're going to do this in 2 steps. On Java 9, I have the same code base with the same class path, and I'm going to compile it. And it works. Yay. Step 1. So backward compatibility for the win, I would say. But now comes the interesting part. We're going to try and to run this application on Java 9. So there we go, it's starting Spring, and class not found exception, Java X XML bind Jax B exception. Well, this is an interesting stack trace. And all the way up the top, it's probably trying to do something with XML because it has a Jax B exception that it tries to look for. Error when creating my session factory. Ooh, this doesn't look good, right? I mean, it was supposed to be so simple, and we were supposed to be backwards compatible forever, etc. But, well, apparently that's not the case. So let's see and try to find out what's going on here. Because we had this Jax B exception that was just normally usable and available in Java 8, and somehow we could compile, but we couldn't run on Java 9. So there are typically two problems that you can run into when you try to run your class path-based application from Java 8 on Java 9. One has to do with the fact that not all platform modules that are in the JDK are available from the viewpoint of your application class path code at compile time. So these are the unresolved platform modules that we'll talk about. And this is the root cause of the error that we just saw. Then there's a second class of problems that we also will investigate, and that is the abuse or the use of platform internal details. And Paul already mentioned this. There's lots and lots of code around that uses types from the JDK, internal implementation types. And because there was no strong encapsulation in Java 8 or before, you may have gotten a warning, but really that's it. You could just use the types. But with Java 9, you can't. So there we go. Let's look at the first problem of those platform modules that are in the JDK, that are in the platform, that somehow you cannot use their code. Why is that? And before we look at the solution of our little problem that we just saw in the demo, we're going to sort of create a little example that showcases the problem in more detail. Now, here we have a very simple class, right? We have a public class main with a single import of Java XML bind data type converter, which is a public class that is exported from the Java XML bind module. So you would expect this to work because by default, when you compile code on the class path, it can see all the publicly exported types of the modules of the Java platform. That's how they guarantee interoperability with old code where you don't have any module descriptors yet to explicitly say, okay, I use these or these modules from the JDK. But somehow it complains to us when compiling on Java 9 that this package Java XML bind does not exist, even though we know it exists because we used it in Java 8 and it was just there and it's not now. So what's going on there? We have this modular JDK, and Paul already showed this picture, at least partly. And there's two roots here, which is very interesting. Well, actually, there's one root, but there's two nodes that act as root. There's the Java SE module, and this one points to essentially all the modules in the platform, because transitively from this root you can reach all the other modules, including the Java XML bind that we were just talking about, and things like Corba and annotations common and XML WS. These are all enterprise technologies that have been added to the standard edition of Java. So Java SE is sort of an aggregator module that points to all the modules in the platform, including these EE modules. There's also the Java SE aggregator module, which also points to almost all of the other modules in the platform, except those EE technologies like Corba and Java XML WS. Actually, the list is here. So there's 6 modules that you can reach from Java SE, but not from Java SE. And what happens at compile time when you compile code on the class path, dus on Java 9, is that it takes Java SE as the root module of all the visible modules that you compile against, and not Java SE EE. And that is why our code, by default, cannot see the Java XML bind classes. You might be wondering, okay, why is this? It sounds strange, right? Because usually you would be able to just use all classes that are in JDK, and now we have some sort of subset. And this is mostly done for interoperability and backwards compatibility with application service. Yes, they're back to haunt us again. So the application service typically have their own versions of these EE technologies as a jar on the class path. Now the problem with this is that if you have a jar on the class path containing code in packages that are also somewhere in a module in the platform, then the Java compiler and the Java runtime will just ignore whatever you put in the class path and just use only the package definition of the package that is in the module, and not that's on the class path. That's a bit unfortunate, right? These application servers would certainly have, for example, alternative WS implementations on their class path, and that would just be broken. So sort of a judgment call was made here, and it's a tough choice, but in the end they said, okay, we're going to run the compiler and Java runtime by default if you're in class path mode against this subset of modules that's reachable from Java SE, not Java SE. So that's what we're up against. Now, you do not need to find this out at compile time or at runtime. You can also use JDEPs, the tool that I already mentioned in the first half, to find these problems before even trying out Java 9. So if I were to run JDEPs on this main class that we just saw, it will give me back the dependencies of this main class in terms of module dependencies. And it would say, okay, you have a dependency from your main class on java.base, and you have a dependency on some module that I cannot find. And this is due to the Java XML bind package on the last line, as you can see. So that already shows us that something is up. Unfortunately, there's also a solution. So what you can do when you compile this code, or when you run this code, is that you use the add modules flag to explicitly add the Java XML bind module, or any of the other 6 EE technologies, or even Java SE to get them all together, visible at compile time and runtime, to the add modules flag. And if you do that at compile time and at runtime for this code that I've shown, then it actually works, and you will get the same behavior as in Java 8. So, should be easy, right? Our compilation already worked because the code that we have in our example application doesn't directly reference the data bind XML code, but it's only happening indirectly through our dependencies. So we only need to add the add modules to our runtime statement, to the Java statement. So let's try that. There we go. Add modules java.xml.bind. And we're going to invoke the script. It's starting, and unfortunately, or maybe fortunately, we're getting a different error. So we seem to solve the first problem, only to run into the next problem. It's the story of my life, it seems. Anyway, there we go. Here's the meat of the problem. It says we have an inaccessible object exception. That's cool, never had one of those. Unable to make protected final Java lang class, some method on class loader, define class. Somebody's trying to make this accessible through reflection using set accessible. And, well, the problem is you cannot just do that in the module system, because even though Java lang class loader is exported and public, doesn't mean that you are allowed to grab into the private fields and parts and methods of this class, which again is a big difference to how things were in Java 8, where you could just essentially use reflection to gain access to anything. And of course, that sounds like a security problem in the making, and we've seen that with all the zero-day exploits of the Java platform, etc. Lots of them use reflection to get access to, for example, unsafe, and then just, well, your system is blown, right? So in Java 9, encapsulation isn't just about which code you can refer at compile time, but it also checks at reflection time whether you can do stuff. So in this case, we have this library that's trying to do something on a protected method of the class loader class, and it cannot do that. So let's go back to the slides and look at a slightly different but related problem, only to come back to see how we can solve this problem. So one of the big problems is using encapsulated APIs. And it doesn't have to be your code, right? It can also be a library that you use that uses encapsulated APIs of the JDK, and it will feel just as hard. But in this case, let's say that we have a Sun Security X509, X500 name class referenced in our code. Who doesn't use it, right? We all know it. Anyway, this is something that you can use in Java 8 because it's just there and you can compile it. But on Java 9, it will say, well, this package doesn't exist because it's encapsulated in a module in the platform. It's not exported, you cannot reach it. Again, you can use JDAPs to find these problems before compile time, before runtime. And in this case, you can add the flag JDK internals to JDAPs, and it will give you a report of all internal APIs used by your code. And if you provide your dependency jars to JDAPs as well, it will also scan those. So you can find out about problems. And the cool thing is, it says, okay, you use this JDK internal API, the Sun security stuff, but there's also a suggested replacement. So you should use Java X security of X500, X500 principal, which, by the way, is already in the platform since Java 1.4. So why are you using this stuff? Now, the best thing to do here would, of course, be to rewrite your code and use the public API, which you can do if it's your own code, or maybe you can't do it because you don't have time or you don't want to. So obviously, there should be a workaround for this. And there is. We'll see that. But first, let's try out and see if we can be smart, because we all finished high school, right? So why not just try to compile it with 1.8? Because we could just compile it there and then just run it on Java 9, right? Well, then you will run into the same problem only at runtime. In this case, you will get an illegal access error saying you're trying to access a class that's encapsulated, and you cannot do that. Same problem, only now at runtime instead of at compile time. And there's a solution to that. And in this case, it's adding the add exports flag, where we indicate that we want to export something from java.base. And the thing that we want to export is the Sun Security X509 package. And we want to export it to, that's a good question. Because we're on the class path, we don't have any module defined yet for our own code. So we cannot say we want to export it to module my application, for example, because it's not there yet. So there's a special placeholder called all unnamed, which stands for all code on the class path. So what we're saying here is that we want to export the Sun Security X509 package from the Java base module to the class path so it can use this code, and we don't have to rewrite our code or change our library or whatever. Let's go back to the code, because it's not quite the same exception, right? It's not an illegal access exception. We have something different here, but it's related. What we see here is that we're trying to we're trying to use reflection on a field that's protected on something that is exported, so we don't need the add exports flag, but we need somehow to gain reflective access to the contents of this package, which by default is not possible. And therefore, we can use the add opens instead of add exports. And if you open a package, it means that you gain privileges to call set accessible on any private, protected, or whatever field and get access. Now, we're using this add opens on Java base again, and we want to add this capability to the Java lang package. And we need to define a target again. So we say all unnamed, because we're still on the class path. So we're adding the capability of deep reflection to the Java lang package coming from the Java base module for all code on the class path. Now, with this out of the way, we're going to run the application again. Oh, ik heb hem, I used it on the wrong position here. Mixing up the arguments and the flags now. There we go. And with this fix in place, we can run our code and nothing breaks anymore. So that is a bit more involved than you might have expected, right? because we just had some code that was running on Java 8, and it used all kinds of libraries, which we weren't really clear what they were doing. But it turns out they were using Java XML bind, even though we don't really know about that, so we had to add this. And we had to add the ability to break into the Java Lang class loader by doing this add opens. So with that out of the way, let's go back to the slides again. Because this is the mental picture of the application that we have. It's a Spring application, so we have sort of these packages correspond to these sort of boxes that we have on the slide here. We have a Books API and implementation. We have this main module that is using the Bookstore and the Books API. But at runtime, we saw this big fat list of jars, and everything is just mixed together in the class path. And wouldn't it be nice to also have modules for this application? So we can actually create 4, or maybe more, or maybe less modules out of this application with explicit dependencies, etc. But this time, we would still like to be using Spring and Hibernate instead of doing a complete rewrite and using the service loader and the things that we saw in the first half. So that's what Paul is going to show us now, how to take this class path-based application and move it into the modular world that we saw in the first half of this session. So take it away, Paul.
All right. So before we dive into modules again, it's probably good to also mention that this might feel a little bit painful, right? I mean, we had an existing working application, and now we just want to start working with Java 9, and it all breaks. But it also has something to do with the whole stack that we're using. I mean, we chose to use the Spring Hibernate stack and a little bit of a traditional Spring Hibernate stack, and that was never really designed to work in a modular runtime at all. And that's why we run into these problems. But it's also the reason that we choose this stack, because that's what a lot of people use. And we actually want to show that even with a stack that was never designed to be used in an environment like this, we can actually still get it to work. The other important thing that we have seen is that we can, if you want, still just use the class path and completely ignore modules. And in the break I also had a question about this. It seems to be quite a bit of work to rewrite stuff and move them to modules, but it's important to remember that you don't have to. So sure, if you write a new application, start using modules, that's for sure. If you have existing code and that's still actively being developed, well, probably you want to migrate that as well. But if you have some kind of code base that nobody really cares about anymore and you're just doing, well, some maintenance on it maybe, but not a lot, you might consider just leaving it on a class path and be done with it. That's all fine in Java 9. But anyway, of course, for today we do want to migrate to modules. So let's dive into that. And the first thing that we will be looking into is just a very simple example. So in this case, we have an example with just a single main class, and this main class has a single dependency on commons lang. I first want to show this very simple example so that we can focus on one specific problem of our setup. Once we have seen how this actually works, we will go back to the Spring Hibernate application and apply that, well, in a bigger scenario and see how it works there. So currently I have a demonstrator, and this demonstrator runs together with this dependency on the class path. And we are not really using modules at all yet. Well, it's not entirely true, because the JDK itself, of course, is already modularized, and it means that Java base, which we always depend on, is actually already a module, but we don't really see that. And what I want to do now, I've seen all this beautiful module descriptors, etc. So I want to take my code, put it into a module, and start using all this goodness. And this application currently is just a single class, and this main class. And I'm using the leftpad function here from string utils. And I've learned from the NPM world that if you want to use something like leftpad, you do need a dependency for that. So that's what I did here. So I'm using commons lang for that. And if you want to build and run this application, we used class path flags both for Java C and Java to add commons lang so that we can, well, see those classes. This is just what we already know, and this would actually work perfectly fine on Java 9 as well. But now as the next step, I want to take this code, put a module descriptor with it, and make it a valid module. But as soon as I start doing that, I run into a problem. I will notice that from my, well, now module, I can't actually access anything on the class path anymore. So the class path is still there in Java 9, but as soon as we move towards that module world, we can't see anything on the class path anymore. And that's a big problem because, well, what do we do now? The only thing left for us to do is, well, move commons length to be a module as well. Well, if it's just commons length, that would be fine, right? I mean, we can actually just clone the source repository, add our module info, and we rebuild it again, and it's all good. But let's go back to our Spring application. We had like 30 dependencies. Do I really want to go into 30 dependencies and add module infos? That doesn't sound right. So do we then just wait until the whole community around us moves towards Java 9 and all those dependencies that I have are valid modules? Well, that's probably also not a very good idea. So what can we do here? Well, they saw this problem in Java, in the ecosystem, and the JDK team added a really smart solution for this, which is called automatic modules. What we can do is we can take a plain jar file, and with a plain jar file I mean a jar file that doesn't contain a module info, and that can be a jar file compiled with Java 7 or Java 8 or Java 9, it doesn't matter. It just doesn't contain a module info. We just move this jar file from the class path to the module path. So probably that just means moving it to a different directory on my file system. And as soon as we do that, and this jar file is part of now part of the module path, it becomes an automatic module, and that means that we can actually use it as a module. It gets a module name, and that module name is derived from the file name. So basically it just looks at the name of the jar file, strips off versioning information, and that's your module name. This automatic module also exports everything. So all the packages contained in this jar file are exported. That also means it's a very bad module. I mean, there's no encapsulation at all, and all the implementation packages that might be in there are exported as well. But of course, the JRE can't actually, well, see what packages are meant to be shared with others and what packages might actually contain implementation classes, so the best thing they can do automatically is just export everything. And it also reads every other module. And that's important because on the class path you can kind of assume that you can see everyone else. And that's still the case on for a automatic module. An automatic module can even see the class path. So earlier I said a module can't read the class path, that's true. But for automatic modules there's an exception, and automatic modules actually can read types on the class path. So that way they're like halfway in between a module and something that's still in the class path. And that's the migration path that we're going to take here. So we've moved our jar file to our module path. And after doing that, we can start requiring commons lang as if it were a real module containing a module info. We can start using it that way from our code. So we can modify our demonstrator code, adding a module info containing the require that we would normally expect there. And now we can successfully compile and run this application. But notice that we don't have a class path anymore, but we now have a module path. As we will see in a moment, when we start migrating the Spring application, you can also combine the module path and the class path as a, well, migration step, so to speak. But in this case, we only had one dependency, and that dependency is now on the module path, so we don't need the class path at all anymore. So this is really good, because we didn't actually care too much about commons lang. We didn't have to migrate commons lang, but we can still use it in a more modular context, and we already modularized our code. So this is a very important step towards, well, using Java 9 modules. Okay, back to the Spring Hibernate stack. What we will do is we will start modularizing this application, but we will do that by first just creating a monolith module. as we call it. So we just create one big module containing all our source code, exactly the same source code that we've seen on the class path just now. And we will first fix all the technical problems that we will face. As I said before, we are using, well, the current versions of Spring and Hibernate, and they were not designed to be working with Java 9. That's why it's interesting. And we will first fix all the technical issues that we will face so that our code works successfully with modules in Java 9, using things like automatic modules that we've just seen. And then as a next step, we will also modularize the code itself. So then we will get multiple modules, and that's what we actually want to achieve. But we will first focus on the more technical stuff. So to create this monolith module, we will do several things. First of all, we have to declare our exports. The framework has to access our code. There's reflection going on, etc. So we have to deal with that. We have to figure out our requires. So we have to think about dependencies, and that's where automatic modules comes into play again. And we will see that some of our modules will become automatic modules, but not all of them. And I will explain why in a moment. So the application currently looks like the picture on the slide. We have a whole bunch of libraries that we have here. I think there's about 30 of them. And then there's our code as well, probably packaged in one or more jar files. So that's the application code. And what I want to do as a first step is migrate our application code towards a single module. And to be able to do so, we'll have to migrate some of our dependencies to automatic modules. But the rest of the dependencies will stay on the class path. So let's dive into it and actually do this. Go to the correct demo directory. There we go. So let's see how we start out. We still have a lib directory here, and this still contains all our dependencies. We didn't move anything to the module path yet. Right? So this is just the same thing as what we've seen in the previous demo. And if we look at a source directory, it's almost the same as what we had before. But there's, well, to start with, one difference. Because under the source directory, we now have this directory book app. If we open the class path example again, we see that under source, we have our packages. So because we're using modules now, we have this new extra directory here, and that's the name of our module. So our monolithic module that we have is called book app. Inside book app, we still have all our packages, because as I said, at the moment we only have a single module to work with. So all the code that we have is contained in this single module. But we also see that we now have a module info. So the rest of the code is completely unchanged, but we do have a new source file, which is module info. And you can see it's surprisingly empty. So probably that's not going to work. We have work to do here, but let's just first try it and see how far we get. So let's try to compile this thing. And as you see, there's lots of errors going on again. So let's see if we can find out what the actual error is. There we go. We get all kind of cannot find symbol errors, and there's a whole list of them. So in this case, we have the @inject annotation here, and we have a bunch more annotations, and we have application context. So basically, all code that is not in our source code, but is part of our dependencies, it can't find it anymore. By now we should understand why this happens, because as I just talked about, we are in a module now, and a module can't read anything on the class path. Our dependencies are still on the class path, but they're pretty useless now. So for example, looking at my main code here, my main code is importing stuff from Spring Context, but although this Spring Context jar file is still on the class path, I can't actually use it for my code. So what do we do? Well, I think in this case, the answer is fairly straightforward. We have to edit our module info, and we have to add a bunch of requires. So let's actually do that. I've got it prepared, so we'll do a bunch of them. So let's look at the fix here. What we have is still our module info, but it now contains a whole bunch of requires. And besides the fact that we have a whole bunch of requires, that only works because we also added a bunch of jar files to the mods directory. So these jar files were previously on the class path, but I just moved them to the mods directory, so they will become automatic modules. But as you can see, this is just a subset of, well, the dependencies that we have. So why, how do you decide which libraries you do move to the module path and which ones are just staying on the class path? Well, what you want to do is all the code that you directly depend on. So you have compile time dependencies, and well, you know you have a compile time dependency because you're importing these classes. Every time you're importing code, so you're directly depending on it, that's when this code needs to be on the module path. And that's the step where you take your jar file and make it into an automatic module. You could instead also say, well, we're just taking all the dependencies that we have on the class path and we just move everything to the module path in one step. That would actually work, and it would work quicker, so you would have less problems. But in that case, it becomes really hard to actually figure out the correct require statements here. Because, as I said, a automatic module will actually read all other modules. And that means that, well, by using one of them, you kind of get access to all of them, which is very, very awkward. And that would not be the case if they were normal modules. So as soon as then the Spring framework moves to become a real module, well, you would have to do work again in your module info. So it's better to take the pain a little bit earlier, just figure out your requires specifically, and only move stuff to the module path when you actually added a require in your module info. All right, so we have Spring context, transactions, some annotations, some Hibernate stuff. So let's see, after we added those dependencies, what happens if we run this stuff? All right, still not looking that great, but we should have a different error now. And this is actually an error that looks should look familiar. So we have a no class def found error, and it's missing a Java SQL exception. And we have seen something similar with JAX-B in the previous demo. Now, it's a little bit different than what Sander talked about, because with JAX-B, the problem was that JAX-B is part of this java.se.ee module. But looking at the module graph, you will see that Java SQL is actually part of java.se. So why is it not included in my runtime? Because it is actually there. It is part of the standard JRE. Well, the reason is that there's only a dependency on Java SQL because one of my dependencies, one of the libraries that I'm using, is using that. Because there's no module info for those libraries, there's no way for the JVM to figure out that, well, that specific library, probably it's, in this case, it's Hibernate, does have this dependency on Java SQL. Because my code is not depending on Java SQL, there's not really any reason, nobody's telling the JVM, that this module should be loaded. So although it's there, it's not loaded, and hence it's not there at runtime. So that's, well, that's a bit annoying, but it's also very easy to fix. And we can fix that by just adding another add mods. We've seen that before. So let's look at my run command here. And in the Java command, we have another add module. So we already had this XML bind, and now we also have Java SQL. this is probably fairly common to happen once when you start using automatic modules. But just remember this error is really easy to fix. So let's run again. And of course we get another error. Now it becomes interesting. So this is the interesting part. We have an error that says in accessible object exception, unable to make field private in books impl entities book entity. So that is actually my entity class. And well, it can't access that. So what Hibernate is doing, it tries to use reflection to look at the different fields that I have in this book entity, but it's not allowed to do so. So let's take a look at our books impl. The problem here is that Hibernate tries to look at those private fields, and by default it's not allowed to do so. Why is it not allowed to do so? Well, we've already learned that to be able to access a package either at compile time or runtime, that package needs to be exported. And well, we didn't do that. If you look at our module info here, that didn't actually happen here, right? So you might expect that also if you were here for the first part of this this presentation, that you need something like exports and then the name of the package. So that would be books.impl.entities. That would be enough. But actually that would not be enough. Because what this would do is give compile time access to this package and runtime access to this package, so that means reflection access, but only to the public parts of this class. You will not get access to anything private if you just have a normal export. To be able to do so-called deep reflection on a package, and deep reflection means using things like set accessible, or looking at the private parts of a class, we need to be specific about the fact that we want that. And there's well, several things we can do for that. The most easy way to deal with this is to create an open module. And with an open module, we just add a single keyword, open, to our module descriptor. And by that, we make all packages that we have available for deep reflection. And this is important. Those packages are not accessible at compile time, so no one can accidentally start using our implementation packages if you just open them. But they can be accessed using reflection, and even using deep reflection, so that means using stuff like set accessible. That's exactly what we need for a compatibility with frameworks like Spring and Hibernate, because Spring and Hibernate, they use reflection and they assume they can touch anything, because, well, it has always been like that. We can be very specific about the packages that we do want to open and the packages that we do want to export. Because, as I said, we can open a complete module, well, that's the first step, but we can also open specific packages. And by that we can be more explicit. We don't have to say, well, every package can be accessed by reflection, but we can be specific about the packages that we do want for that. So then we get this table where you can actually choose what you want to do with a specific package. If you have a package that is not open and also not exported, nobody can access it. Only your code inside your module can access those types, but nobody else. So not at compile time, and also not at runtime using reflection. And that's the default. If you don't specify anything about a package, it's completely closed by default. And that's exactly the error that we're seeing right now, because we didn't open our package and our module yet, so Hibernate can't access our implementation code. Then we have seen in the previous part of the presentation that we can export a package. And when we export a package, we get compile time access, and we also get reflection access on the public parts of types. right? So if you have a public class with public fields, you can see that, that's fine. But you can't do deep reflection, so you can't use set accessible true. Then we have a second keyword, and we will see that in code in a moment. And the second keyword in the module info is open. And with open, we don't give away compile time access, but we do allow reflection and even deep reflection. And then you can have both an export and an open, so there's just 2 lines in your module info, and then you can just give access any way someone wants. So let's apply that. That didn't work out completely. There we go. All right, so this is actually wrong. This should be open module. So with an open module here, we now say that everyone can access and even use deep reflection on these packages, on all packages that we have, including all our implementation packages. So we're not specific about which packages. We just say, well, we are specific about compile time access, but we don't really care about reflection. And that will be the easiest way to have compatibility with existing frameworks, because existing frameworks, well, kind of depend on this. And without really thinking about it, we can now get compatibility with those frameworks. Remember that this is not true encapsulation. You get encapsulation at compile time, that's good. This is a step forward, but it's not true encapsulation because someone can always just walk around your module boundaries and use reflection to use whatever types in your module that they want. But of course it's a big step forward because now someone really, well, they really need to want to do this stuff, and they need to use reflection to do whatever they want to do. And they will not accidentally depend on types at compile time because they think it's an API type while it's actually an implementation type. So it's a big step forward, and that's actually really good. This is also really important because this, this open keyword is really new. That's just part of the prototype that was released last week. And in the prototype before that, we didn't have the notion of open. And in that case, you would have to export any package that needed to be accessed by reflection as well. And that, by doing that, in the case of Hibernate, we would have to give up encapsulation for our entity types, which are, well, basically implementation types, just because, the frameworks need it. So this is a really nice compromise by saying, okay, I don't really care about full encapsulation, because I have code that requires this reflection, but I still want to make sure that no one uses those types at compile time. So that's really good. So let's see what happens by just adding this single open keyword. And again, we get to a next step, and now we're actually almost there, just looking at this technical migration. Let's find the actual error. There we go. Looking for the root cause. Still not seeing it. There we go. So we are now looking at the weirdest error that we have seen during this whole migration example. And it took me a little bit of time to understand this as well. Even though we kind of understand what the module framework is doing and expecting. But this is really a tricky one. You should also remember this is very specific to, the current versions of the libraries that we're using. And because of that, there's no really nice errors, etc. So you really have to understand all parts of it to be able to parse this. But what happens here is that we have another illegal access error. So we kind of know where to search. Well, we don't have access to a type that someone tries to read. So it's similar to what we have seen previously with reflection, but not the same. So let's check. Someone tried to access a type, and there we go. We have our book entity. Well, so far so good. That's my implementation type, but we just, well, gave reflection access to that. But then, looking at a class name, there's some weird identifier at the end of it. So what happened here is that we are not actually looking at book entity the way I wrote it. So this is not literally an instance of this class, the one that we wrote, but it is actually a runtime generated subclass of this book entity. So what Hibernate does is it uses JavaSys to, at runtime, create proxy objects, which are basically subtypes of the entities that we give it. And those subtypes, that are the types that actually are used during runtime. Very specific to the way Hibernate works and very specific to the way JavaSys works. But what happens in that case is that JavaSys in this case is still on the class path. When it generates this new type at runtime, because JavaSys is in the class path, the new type that it generates will also ends up in the class path, basically, so in the unnamed module.
Well, it's not quite right. It's in the module, and it tries to access the class path, right? Because
See, it's right. It's the other way around. You're absolutely right.
Yeah.
Well, the result is the same. We have a runtime generated type that now talks to the class path, although we didn't really have control over that. And we have already seen that if code is in the class path, if code is in a named module, then it can't access anything in the class path. That's just a rule, and we can't get around it. So luckily, although this error is extremely weird and strange, the solution is actually very simple. The only thing that we have to do in this case is just move JavaSys to the module path as an automatic module. So if you look at our run descriptor, we already had we already saw this before, but we have this add exports private, where we say that JavaSys can now do extra stuff on Java lang. That's fine, and it's also moved to the module path, because if you look here in the mods directory, it is now right there. Just by doing that, we don't have this problem of modules going to the class path anymore.
Still weak module. That's what you get for using the cutting edge prototype that's released just a week ago, right?
Yep, we didn't change it everywhere. After actually fixing this, because that was just because I did another git checkout, we now have a working Spring Hibernate application. So it wasn't really easy. I mean, we've seen several weird errors, especially the last one that we have seen, really requires you to understand deeply how the module system works, and also requires quite a bit of knowledge about how a Hibernate actually works. So that isn't very good, but at the same time, we did get this whole stack working that was never designed to be used in such a restrictive modular environment, and it actually works out really well, quite easily. It was just a few steps that we had to take to actually make this work. So from that perspective, this is actually really good. So just a few tips before we start looking into actually modularizing the code base itself, because that's of course what we want to end up with. The first thing is you want to move libraries to the module path one by one. I've already mentioned this before. You just want to focus on the dependencies that you have that are direct dependencies. So every time you directly import some code from an external package, that's when you want to move this library or this jar file to the module path and make it an automatic module. If you don't, stuff will work out as well, but you will never end up with a module info that actually has the correct requires, which makes it more trouble once those libraries actually do migrate to proper modules. And I think it's just better to take the pain directly and just deal with it, because it's actually not a very difficult thing to do. Then the next thing is, whenever it is required for other libraries to have reflection access to your code, but there's no compile time dependency, use open instead of exports. Try to export just types that are actually part of an API. If you just export everything, it will mostly work as well, although deep reflection still doesn't work. But you will open up a lot more, or lose encapsulation on a lot more than you need to. So be very, very specific and careful about what types you export, because those are types that you should support in the future as well. Those become part of your API, and you don't want to suddenly change that probably. Open is a little bit easier. That's just reflection access. So you can use that a little bit more freely. It's not as big as a deal as an actual export. Then we have also seen that sometimes we are using the requires keyword in our module info to create a dependency on another module. But sometimes we just add it to the runtime by using add modules. Let's say that this case of Java Assist, for example. We have a runtime dependency on Java Assist. I could have just added Java Assist to our module info by using a require. And this would actually make it work correctly. That's fine. But in that case, I would have a dependency from my module directly to Java Assist. Although I'm not actually using Java Assist in my code, but one of my dependencies is using Java Assist. So it's a transitive dependency of some library that I'm using. I'm using Hibernate directly. Hibernate is using Java Assist, and that's why I need it, but I don't have a direct dependency on it. If I would still write a require Java Assist in my code, I would create a direct dependency. If Hibernate at some point in the future would move away from Java Assist and use some kind of other library instead of Java Assist, I would still be stuck with that dependency on Java Assist, and I would never really know when to get rid of it. So just use a require when you have a direct dependency from your code to some other module. If there's just a transitive dependency and a transitive dependency that was not added to the module graph yet because this dependency that you're using was not a module yet, prefer to use add modules.
I think it's also good to add that a lot of the problems that we've seen here are early adopter problems, right? Just because Hibernate and Spring don't have module descriptors yet, we have to pull a lot of tricks to get it working. However, if we are going to use Hibernate when it's a module, and Spring when it's modules, and they're going to do that. Spring is actually actively looking into defining module descriptors for the jars. And a lot of those problems will disappear because those jars will have the correct module info descriptors, and we don't have to care about all these transitive dependencies anymore. That's taken care of by the module system itself. So while what we're doing here is the right thing to do, it's also more painful because we're doing something that's ahead of the curve currently. So.
Yeah, absolutely. Finally, it's a lot easier if there's frameworks that depend on reflection and you're using them. You probably know that. You know that you're using things like Spring and Hibernate. You probably know, or you should at least know, that they do use reflection on your code. It makes things a lot easier if you just put an open on your module, so that those frameworks can just access all your code, and you don't really have to specify that specifically. But you do want to come back to that module info and fine-tune it a little bit later on. Actually, we didn't go to that step yet, but let's take a look at it. So one more chance to our module info here, and this is not right either. So this export private is from the previous prototype, and somehow that didn't work out with Git very well here. So the difference with what I had previously we had this open module book app, and that means any package in my module can be used for deep reflection. If we remove the open keyword, that means it's just a normal module, and in a normal module, everything is inaccessible by default, both at compile time and both at reflection. So we have some API types here. Those are exported. That's for compile time use. That makes sense because they're APIs after all, so that's what we want to share with the rest of our system. But then for our implementation types, which are just, well, just Spring and Hibernate need access to those using reflection, we use open instead. So there's no compile time access there. So in this case, we don't give away reflection access to just, well, any type, but we'll just do that for the specific types that have this issue right now. Then there is one more thing that we could be doing. We could be specifying who exactly should have reflection access to those packages. So in this case, we open it up for just, well, anyone else. But we could also say open this package to, for example, Spring Context, if you know that Spring Context is a module that actually requires this kind of reflective access.
It should be opens instead of opens.
Yeah, typo. Yeah. Then it probably also didn't run. I didn't even notice that.
Spring.context. Yeah.
So there's another thing you can do. You can use qualified exports, both on open and on exports, to be very specific about a specific module that should get access to your packages, but no one else. So we have several options there, and you should definitely use those options. But let's go to the next step, because we did get our frameworks to run again, and we did well, make our code to be a module. But did we really, well, improve our code a lot? Because our code is just the same monolith that it always was. So although we are now in a module, well, we are not reusing the benefits of modules. Actually, that's not entirely true. Because what we did get is that we get more reliable configuration by setting up our requires. Now, the JVM does actually know and can check if all our requirements, all our dependencies are actually there. We are still in this mixed class path and mixed module setup here, so that we don't get fully reliable configuration. If we mess up something on the class path, our application will probably still fail. But at least it's a big step forward. And once more of our libraries actually move towards being, well, real modules, that will get better and better. But of course, it would be nice if we can also improve the source code itself and make the source code itself more modular. So what I want to do, this is the situation we ended up with. So we have our big monolithic module containing all our application code, and I want to split that up into several modules. Of course, in this specific example that we have here, you might wonder, well, is it really worth the trouble? Because, well, it's just a few classes, and do we really have to modularize that? And of course, the answer is, well, probably not. If you just have a few classes, it might not be worth the effort. But let's assume this application is actually a lot larger than this demo application, and then it definitely pays off to have more smaller and more specific modules. So in this case, we will end up with a main module that just contains my main class. I've got a books.api module, just containing the APIs of book, so that's the book service and book itself. We have books.impl containing the Hibernate code and the actual entity to work with Hibernate. And we have a bookstore, which contains both the API and the implementation of the bookstore. So let's take a look how that looks like in code. Before I forget, we'll also move there. And if we now look to this final demo that we have here, you see that the structure is actually quite different. Remember, the first directory level under source are still module names. So these are not packages, these are module names. So we have our 4 modules here: main, bookstore, books impl, and books API. And if you look at them, they will all have their own module info. So this is already looking at a structure, a more modularized setup that we have here. If you look at a main class, it's still doing exactly the same thing. So it's still using the Spring application context. It's using our book service, but as you can see, that's just the API. It's also using the book, also coming from an API package, and our bookstore service, which is also an API package. If you look at our module info, that looks a lot cleaner now. So previously we had a whole bunch of requires to, well, pretty much every library that we were depending on at compile time. But in this case, we just have Spring context, books.api, and bookstore. We have Spring context here because we are bootstrapping this application context, so we have a direct dependency on that. We are using the book class and the book service class directly, and bookstore exports this bookstore service. So these are the direct dependencies of this main class. You also see that there's nothing about, let's say, Hibernate anymore. This main module doesn't use Hibernate, so, well, you don't need a require for that either. There's no dependency to Hibernate here. So something else that's, well, interesting, and that's also a choice to make, is that we have this book.api module. This book.api module is just containing our APIs. So the entity that we have in the Spring implementation for the book service is not part of this API module. And it also means that looking at this module info of books.api, we do export those packages because they are APIs after all. So that makes sense. But there is no requires on Spring or Hibernate or whatever. This is just API. And the implementation is just a completely different module. So in this module, we do require Spring transactions and Java or Hibernate, for example. And again, we have this opens here. So in this case, we do open up our implementation packages again. And as you can see, we also require our own books.api. Even in your own code, of course, if you want to use, well, code that is not in the actual module that you're currently looking at, you need to require it. So why did we split up this API and implementation module into 2 different modules? Why not just put them together? Because if you look at the bookstore, we see that the API and implementation are actually in the same module. And again, we can be specific about what we export. So that's just our API. And our implementation classes are just available for reflection. So this is a choice to make. And both are valid options. So you can either have a specific separate API module, that's fine. And that's often a better choice if you expect multiple implementations of the same API. Because all those implementations can then depend on your API module without also dragging in a default implementation, for example. And users of those different implementations that we have can also just depend on the API without requiring a specific implementation. And we have actually seen an example of that when we were playing with services in the first part of the presentation, where we would have a service for the different analyzers that we had implemented. In a scenario like that, it's a good choice to have a separate API module. If you have code that will probably never get implemented with a different implementation. It doesn't really help at all if you separate that API, and you can just put them together, and that's fine too. So that's the example here that we have in the bookstore. So both are fine. Just think about the users model. The other nice thing that I have here is that all the implementation details about the fact that we're using Spring and Hibernate for data access are hidden away in my implementation module. And they're not spread throughout the code base. And for example, our main module doesn't really know and doesn't really care about it. A little bit more Spring specific, but nice anyway, is that you can potentially also split up your configuration. So in this case, you have a Spring XML file, and I know there's different ways to use Spring configuration. But in this case, this book Spring.xml contains things like data sources and stuff like that, because we have this data access stuff here. But for example, looking at the bookstore, it's a Spring configuration with just a component scan. So again, this is a little bit Spring specific, but even configuration is something that you can really nicely split up and put in the in the specific module for it. Well, I think this is a much nicer setup of a project. Here we have several small modules all doing their own thing, hiding away implementation details, because, for example, in Book Simple, I could just get rid of Hibernate and replace it with some completely different persistence strategy, maybe even not work with relational databases anymore, and the rest of my system would remain unchanged. And I think that's a really powerful thing to have. All right, so we managed to do this as well, and you've seen that actually that's a fairly small step, you could say, after you get the technical things working. And that's why we also advise that you take this kind of migration in several steps. So the first thing that you should do if you start looking at Java 9 modules and you want to migrate your code to Java 9 is to just migrate to Java 9 using the classpath. So that's the part that Sander was talking about. Hopefully there are not, maybe there are not any errors, because if you're not using any kind of encapsulated packages from the JDK and not some specific errors that Sander was talking about, like the one with XML, you probably can just run your Java application on Java 9 the same way as you've always been doing. So that's a good option, and then at least you know you don't have this kind of encapsulation problems, right? Then the next step is, okay, now we do want to migrate to modules, and for that we are first going to create a monolithic module. So just a single module containing all our source code, and we're just going to focus on getting the requires correct, and work on that part, making sure that we have the correct access set up for reflection, for example, so we can use the open module or open packages. It's an important step, and once we once we are done with all those technical details, and as Sander also mentioned, the number of steps required to get such a migration working will probably become less and less as soon as the frameworks get better support for Java 9. So if you upgrade to a newer version of Spring and Hibernate, for example, things just might work out of the box. And then finally, and this is of course the end goal, is you want to modularize your own code base, because then you really get the benefits, and that would really be a huge step forward. Then you might also wonder, so okay, this seems to be fairly easy, but it's still a lot of work, especially if your code base is a lot larger. Do I really have to do this when I want to start using Java 9? What if I just want to migrate to Java 9 to use some of the other features in Java 9, but I don't really care about modules? And as we've seen, that's fine. You can just use the classpath with a few caveats, but in general, it just works fine. And that's a valid choice. I would say if you start building new code, use modules. if you start doing that from scratch, it's actually fairly easy, and it helps you getting this nice modular architecture that you draw on a whiteboard and actually translate that to code. It's not easy, it's not a lot of work, but it's a very important step. If you have a code base which is still under active development, I would say, well, take these migration steps, get it to work, and it's probably still worth the investment to migrate to modules. But if you have some kind of system that, well, maybe sometimes you still fix a bug on it, but besides that you don't really care about it anymore, it's not going to be actively developed anymore, you could just decide to just leave it on the class path. That's absolutely fine. You don't have to migrate to modules as soon as Java 9 comes out. But that being said, of course, if you start writing new stuff, start using modules because they're pretty cool. With that, we're out of time, and this was also everything we had to show you. We already talked about the book. The book is already available in early access. That means that you can actually buy it, and it will get updated every time we push a new chapter. In the end, you will end up with a whole book. All the code that we have shown, both from the first part of the presentation and also the second part, is available on GitHub. And we have this Twitter account where we post news about the book and Java 9 in general that you can follow to keep updated. With that, thanks very much for your attention. If there's any questions, please use the microphones so that they also end up in the recording. If you don't want to use a microphone, you can also just come forward and ask that after we're completely done. Well, thanks a lot.